like that. Am I getting a, no, okay. Sorry. Clicker. Where did the clicker go? I mean, I know how to do that, but yeah. Here, we found the clicker. Excellent. So now that the area directors have noted where the clicker is to advance the slides, please note the note well. We're learning a lot of things at the IETF, apparently. And we are not on, oh, that's right, I changed it to morning session 2, but forgot to change Tuesday, so we're doing that. But this is our agenda. Would anybody like to bash the agenda before we get going good? Not seeing any rush towards the microphones. So this is what we will be doing. We have some administrivia to do, which we always do. We're talking again, and this is for the first time in a while, but Tsvarea is often doing forward-looking talks about things that may affect transport and the internet, not necessarily things that we're looking to bring into the IETF at this point, or bring into, or not looking at things that we are looking to bring into a TSV working group for standardization at this point. So we have 3 talks there, which are, I believe, all more or less related to discussions that they're having in the art area about, we didn't used to think, mumble years ago, that HTTP was a particularly good transport substrate, but that HTTP is not a particularly good transport substrate, but HTTP has changed a lot since then. And now we're rethinking some things. So you're looking at like BCP 56 bis as draft names over there and things like that. And I believe all 3 of these talks are kind of growing out of that conversation. We wanted to, when they talked about them in the art area meetings, people asked transport questions. So we asked them to come here, and we hope that we will not be having transport people asking them art questions. And then we do hope to have some time for questions and answer. And we always say it is not too soon to start blaming the outgoing area director. Hi, I'm Spencer Dawkins. I'm the outgoing area director for the transport area. And we wanted to recognize the review team and actually welcome Gori, who has joined the review team now, and recognize the people who have done reviews, and a bunch of people who have done reviews. And we appreciate that, including even one of the triage team members, Magnus. We're still recruiting additional reviewers. You'll see here that most of the people on this team have done at least 1 review since the last IETF meeting. So, they haven't done 8, so it's not a desperate problem, but it will be good. It will be good to make sure we have spare capacity during on this review team. We have our usual thing about working groups, and what I'm actually talking about for my groups is what we're talking about at this meeting. So DTN. This whole version of the slides. Let's come back to these. This is what we've done, publishing RFCs and getting things approved and things like that since the last IETF. No, these are real old. Cool. This is new. So a good thing to mention here is just. This is the slide we put up in IETF 102. The NOMCOM has gotten nominations in for positions that they are reviewing, and they are collecting feedback this week. Adam Roach, who is the ISG liaison to the NOMCOM, came and begged me to ask everybody that I talked to provide feedback to the NOMCOM this week, because they're doing all the nominee interviews this week, and then they are starting deliberations like next week. So the more that they know when they start talking, the happier they will be, and the happier you will be. What else? So I think we are ready to start. I don't know if we have a note taker. We'll stop for a moment and find a note taker. Did I see a hand go up back there? Or was somebody just stretching? Wait. Oh, Magnus has his hand up. What? This guy's a superstar. Please tell the non-com that. So excellent. So that would take us to, and I will let you try for a moment. I'm uploading slides or something, aren't I? Yeah, that. Oh, those. And actually, do we have stuff uploaded to present yet?
Yeah, I have uploaded that.
Oh, okay, perfect. So I'm just uploading church slides. Perfect.
But the first presentation is going
I'm sorry?
first presentation is
Okay, cool. I think that's right. I'm dragging this out so that we can monitor this. Yeah, Catherine is the first.
Yeah, Catherine, can you come to the front already? Thank you. I'm trying to get your slides here.
Hey, Catherine.
And the clicker for you.
Yes, you are now running the meeting. Make good choices.
All right. Hi, everybody. Thanks for being here. Today, I'm going to be talking about proxying and hopefully motivating future work for UDP proxying in particular. So this talk is related to a couple of presentations that were given at the last IETF in Montreal. Ben Schwartz gave a presentation on helium and dispatch, and Lucas Pardue gave a presentation on hint and HGVIS. So if you saw either of those, you might be a bit familiar with what we're going to talk about today. But if not, no worries, because I'm focusing mostly on the problem today rather than any solutions. So I'm going to start by talking about the basic feature requirements for a specific use case, and then I'll talk about how those requirements are met currently for TCP proxying, but not necessarily for UDP proxying. So the use case that I want to talk about is inconspicuous proxying. Now this is the concept of proxying in such a way that you can't really tell that proxying is happening. So on the top half of the slide, basically you want the traffic that's proxying traffic between the client and the proxy to not be distinguishable from normal internet traffic. And ideally, this traffic on the link between the client and the proxy would look like typical web browsing activity. We don't really care what the traffic looks like between the proxy and the destination, because in our threat model, the middlemen that we're interested in are on the link between the client and the proxy. The second component is in the bottom half of the slide, and this is where you don't want the proxy itself to really be indistinguishable from other standard internet or infrastructure. So ideally, it would look like a web server. And I guess one other thing to mention here is that when you proxy traffic in a way that it's inconspicuous, then blocking by middle boxes is harder, and this blocking could be either intentional or not. Of course, when it's intentional, this is the standard censorship case. So on this slide, I have a list of 5 features that are kind of, the basic requirements for inconspicuous proxying. They're certainly not all-encompassing. So first, we want the traffic between the client and the proxy to be secured, to have the typical security properties. You shouldn't be able to figure out the ultimate destination, and a third party shouldn't be able to observe or manipulate any of the traffic between the client and the proxy. Second, as we talked about on the previous slide, the proxy traffic should blend in, and ideally it should look like standard web browsing traffic. So third, the proxy should attempt to maintain similar performance characteristics for the proxy traffic as non-proxy traffic would have. So for instance, if a client wanted to send traffic to a destination with UDP-like characteristics, then both the link from the client to the proxy and the link from the proxy to the destination should both have UDP-like characteristics. If either of those links had TCP-like characteristics, then we wouldn't really be, maintaining the UDP-like characteristics that the client really wanted. Okay. Fourth, the proxy should have an authentication mechanism. This is pretty standard for proxies. It shouldn't be willing to transport or to proxy traffic from a client if the client hasn't authenticated properly. Fifth, the proxy should be resistant to active probing attacks. Active probing attacks are cases where a third party sends a manipulated packet to a piece of internet infrastructure to try to gain more information about it by looking at the responses that the proxy or the piece of internet infrastructure returns. We don't want the proxy to be identifiable as a proxy, and ideally it would look like something else like a web service. So perhaps that means being able to serve a web page on port 443. So there are solutions out there that work pretty well for our use case for proxying TCP traffic. And on the next few slides, I'm going to try to demonstrate how you can use an HTTP proxy to meet those 5 features on the last slide. So let's say that you have a secure web proxy, meaning that the client is going to perform a TCP handshake and a TLS handshake with the proxy before it sends its connect request. I guess I should note that these slides are for HTTP 1.1, but it's very similar for HTTP 2. Because the TLS handshake occurred, the connect request will be encrypted. And assuming that the proxy does a successful TCP handshake with the destination, then any data that is sent later on between the client and the destination should be encrypted, at least on the link between the client and the proxy. There could be an additional layer of encryption between end-to-end between the client and the destination if the destination is using TLS, sorry. Okay, so that's basically requirement number 1, securing proxy traffic. Now, if we look at the traffic between the client and the proxy, what does it really look like to an outside observer? It looks like TLS over TCP over IP. And this is basically what web traffic looks like. Now you could get more sophisticated and perhaps look at things like packet lengths or packet timing, and then maybe at that point you could realize that this is proxying traffic and not normal web traffic. But at least to some approximation and for some reasonable threat model, this satisfies requirement 2 that the proxy traffic is blending in. Okay, for the third feature, which is similar performance characteristics, we're talking about TCP proxying here, so it's basically sufficient that TCP is being used as the transport between the client and the proxy, as well as the proxy and the destination. Okay, and the last 2 requirements that we need were proxy authentication and active probing resistance. So typically, if you have a proxy and the client issues a request and either includes no authentication information or includes the wrong authentication information, the proxy will typically respond with a 407 error code requesting proxy authentication. This obviously gives itself away as a proxy. So, if you're trying to do inconspicuous proxying here, you can not send that 407 error code, and you can act like a web server instead. If you're wondering, the draft that specifies the 407 uses a should rather than a must in this case. So I think it doesn't actually conflict with the standard. And for the proxy to act like a web server, it should also be able to serve a web page in response to a GET request on port 443. Okay, so that was all for TCP proxying. And without getting too much into the solution space, what would a potential solution look like for UDP proxying? Well, first we would want UDP properties on both the client to the proxy link as well as the proxy to the destination link. We would want the traffic between the client and the proxy to be secured. So perhaps this means using DTLS or QUIC. We would want active probing resistance and proxy authentication for the proxy. And as we've been saying, ideally it would look like a web server. And the traffic between the client and the proxy should look like typical QUIC traffic. So there are certainly solutions out there, some standardized, some not, that deal with UDP proxying. And I thought it might be constructive to talk through some of those and try to explain why we think they don't meet our use case, and perhaps also help motivate why we want additional work in this area. So first up is turn, which has come up a lot in previous discussions around hint and helium. So to secure the traffic, we would need to use DTLS over turn, and perhaps this would look a little bit like WebRTC traffic at that point. There's a question, though, as to whether the entirety of WebRTC traffic provides enough collateral damage or is it sufficient cover for our use case? Certainly in the long run, it seems like a better bet for us to blend in with QUIC traffic, QUIC web browsing traffic. Also, apart from what the traffic itself looks like, operating a small turn server could look suspicious. Most turn server deployments are rather large and associated with a small number of well-known services. Okay. The next protocol we might consider is SOCKS, which supports both TCP and UDP proxying. There's a new version of SOCKS being discussed currently that would support DTLS. But this would not blend in well with QUIC web browsing traffic at all, either the traffic component or the SOCKS proxy. That wouldn't really resemble a web server. And I think running both SOCKS and HTTP on the same port would not be a good idea. Okay, lastly, there are various existing VPN protocols that support UDP proxying, but these are generally fingerprintable, so they wouldn't, the traffic itself wouldn't blend in with web traffic, and the VPN would not look like a web server. So for basically the same reasons as SOCKS, we don't think this meets our use case. I'd definitely be interested to hear, though, if you think there's an existing solution that kind of meets the 5 requirements. Yeah, so this is everything that I have for today. So the 5 features that I've kind of been harping on kind of represent a minimum feature set that we're interested in. And there's certainly other aspects to this problem that we find interesting. And if you've seen the Helium draft, you may have an understanding of what those are already. If anybody has use cases that overlap with the features that we've been talking about, that would be very interesting to hear as well. Thank you.
Yeah, thank you very much. I should have mentioned that before. So we have 2 more presentations, short presentations, which will go further into detail and talk about more use cases. So we can have like a high-level discussion about the general concepts after the 3 talks, and we can have some specific questions to this talk right now. But if you have like a more general comment, then maybe hold up for after the next presentations.
Well, yes. I mean, you're presenting the requirements for proxying, and we did a very similar exercise in the TLS working group when studying the requirement for SNI encryption. And we have a draft that is in working group last call right now on listing all the requirements for SNI encryption and going in great details about ways to do that. And I think that it will be very much related to what you're doing.
Okay.
Hi, David Skenazy, Google. I just wanted to say that this is really great work. I find it really interesting. And if there's any way we could make this working quick. I think that would be amazing. Thank you.
Thank you.
So, next. Thank you. Oh, look this up.
Eric Kinnear, Apple. I agree. I think this is really interesting. I can think of several use cases that would be very helpful to be able to proxy UDP in a similar way as people do TCP, especially as Quick and other similar areas start to kind of expand the usable amount of UDP in the world. It would be worth, we may talk more about specific solutions later, so I don't want to get too far ahead, but it would be worth double checking on the some of the datagram stuff in Quick that we're discussing about how to send unreliable UDP-ish traffic over Quick. The other kind of question that I had is when you talk about the HTTP connect where you're doing TLS to the proxy and then potentially even TLS through the proxy, and we talk about that as having similar performance characteristics. If it looks like HTTP, a lot of HTTP flows are fairly short-lived, but the setup cost for that many round trips to get through that proxy and all the way to the end can be very high. On the other hand, if you want a much longer-lived connection, now somebody who's fingerprinting it probably is not as convinced that it looks like HTTP. So it'd be interesting to look at how that trade-off could be alleviated for other solutions that might be able to shave some of that time down.
Yeah, that's certainly something that we would need to consider as being part of the threat model or not. You know, do we want to consider length of connections, timing between packets, length of packets? You know, all these sorts of things could absolutely be used to differentiate between different types of traffic, even given encryption. So, you know, it's just a question of how high we want to set that bar.
Totally agreed. And I think this is really excellent stuff to be thinking about.
Thank you.
Okay, thank you very much. We go on with Lucas, who is unfortunately not here and should join us remotely now.
Hello, can you hear me?
Oh yeah, we can. Go ahead.
I'm not putting the webcam on because I am very jet lagged. So I apologize that I'm in San Francisco and outside of protests related to the unions and the hotels. So if you can hear some noise, apologies for that. I changed the title of these slides slightly from what was on the agenda. I don't want to focus too much on the tunneling aspects, but more just on some of the talk about Quick, which I had a nice prelude to just then in the comments. So if you could go on to the next slide, please. This is a very quick recap with images too small to see on purpose because I don't want to go into them too much. What I did at IETF 102 was present on a little thing called HINT, which is a very wide look at how we could achieve HTTP-based tunneling for something like HTTP over Quick that we can't do right now, and looking at all the possible candidate solutions that I could think about coming up with. And really what that did was look at initiation of a end-to-end association or possible flow of things, and then more of a steady state interchange of that data. And that's really all that was. There's a presentation with many slides that really focus on the use cases here. And as we just mentioned, we've got different security associations. So we've got a client to proxy one, say a TLS or a Quick security association. And within the end-to-end, we have another one there. And indeed, with this kind of nature of HTTP proxying, you can chain those proxies up. So you might have, in a worst case scenario, Quick within Quick within Quick ad nauseum, and that might be something people want. It might not be. I don't want to focus too much on it. But if people are interested in some of the visualization, some of the pros and cons, just a flavor text on that ID, I would encourage them to have a look at that presentation I did last time. But if we're going to move on to the next slide, coming away from that discussion, I wanted to kind of really distill down the capability of what my focus was on the HTTP Connect aspect of things. So what is it really? What's it trying to do? And my view is that it's it's a signal that is defined already that allows us to change the meaning of this client to server hop from a, just
Lucas,
in-
sorry, it got very quiet suddenly. Maybe you get closer to the mic.
Okay, yeah, I'll talk louder. So in HTTP 1.1, we just use HTTP.
Hold on, you're getting more and more quiet. That's actually a problem.
Oh dear, it might be mic gain.
Yeah, can you, like, either we need the meet echo people or
Yeah.
you can try to do something. I don't know.
Well, we can put the thing in mid echo about drop volume level.
Yeah,
Okay,
try to say something again.
is this any better?
No. Sorry, you have to hold on. Are you putting it into Java already?
Yeah.
Yeah, you're not in the, I'm in the Java one.
Do we want to do it?
We have time, let's wait for a little more.
We say meet echo.
Yeah, we already in contact with the Meet Echo team. If you can start talking again and we see what's happening.
Okay, so HTTP 1.1, we use the connect method to change the entirety of that HTTP connection. In HTTP 2, if people aren't familiar, it's the same method, but it just reserves a stream for a particular association. And in HTTP Quick, it's a very similar mechanism, but all it can do is reserve that stream for onward TCP use. So this is kind of the motivation for why I wanted to look at UDP proxying, so we could have a quick world that we can have UDP all the way through. Okay, and so if anyone's familiar, the HTTP to WebSockets bootstrapping was fairly recently standardized. So this is RFC 8441, and this is a slight modification of what connect means in order to enable that. And there were a few options there, but Patrick McManus, taking a view of the community, decided that this was maybe the best way to do things. So what it's trying to highlight is that's how things are done already, and that's how I went into IETF 102. But having had some feedback and seeing what was naturally happening in this space, there's been a few things that I've seen or heard. So if you move on to the next slide, I just want to give it an overview. These are kind of the quick specific addendums that have happened in the meantime. So some of the feedback is that these new uses of streams, if we're going to reserve a HTTP2 or HTTP quick stream, these are guaranteed delivery mechanisms with congestion and flow control, and that actually there's use cases for UDP that may suffer from those characteristics, and that it might not be needed or impractical. And certainly, I work in video related things, so unreliable delivery definitely has use cases here. We don't want to be losing that capability just because we're tunneling. So to that point, both Ian Sweat and Eric Kinnear and Tommy Pauly kind of both came up with this textualization of a message frame or a unreliable datagram extension for quick. And they're both very similar mechanisms to just say, here's a frame type that can be sent within a quick connection context, and it's good. So I think there's been further discussion and stuff going on. There'll be a presentation from Eric, Tommy, or David, I'm not sure exactly which one, later this week at the quick session on this topic. And there's some IDs there in the links. I won't go into those. I'm not an expert, but I think this is really good stuff in this direction of travel. So I'm really interested to see what happens this week on that. I've also had a little bit of discussion or been pointed towards some of the stuff going on in Tor, and looking at a case for using Quick for Tor and calling for an end-to-end solution, not something that just does hop by hop, but to really get a better fit for Quick for Tor that can improve some of the problems that they find with congestion control when it's not applied properly. Meanwhile, we've got Colin and Jorg looking at, say, real-time media over Quick and what that might need from the Quick transport itself. Again, looking back towards these kind of unreliable deliveries, whether that's a datagram message or unreliable streams, really trying to state some of the needs here, not mandating the implementation of them. And then a final point without any link here is this idea of multiplexing different protocols. So there's been work already in this area about how we might be able to multiplex different protocols at the UDP layer. But recently there's a bit of chatter in the Quick space about how you might multiplex different application protocols. So, you know, if you're doing something like alternative services, could you say that this endpoint is offering HTTP and protocol other, and that there'd be some way to differentiate them within the Quick transport, which seems maybe one way to do it. Or if you were able to assign specific meanings to streams or subflows within a connection, say, or to have these datagram frames with a kind of sub-protocol within them, that might help avoid some of the practical problems there, but it adds overhead because there's more framing, those kinds of things. And then finally, just to draw some attention to the world of WebRTC and Quick and TAPS, and there's been a bit of overlap, say, between different groups and what they're trying to achieve. And I think this is sort of been recognized in some of the mailing lists I just lurk on. And so there'll be a bit of discussion on that in the TAP session later this week. I couldn't find the agenda item exactly when I put these slides together, but I'm sure somebody can comment towards that in the discussion. So if we went on to the next slide, just to summarize everything. The IDs that both Ben and I presented at IETF 101 haven't changed. So if you did read them, they're still relevant. There's probably a few fix-ups from our perspective, but yeah, they're as they are. We're learning more stuff, and there's a bit of momentum in this area, which is a good thing, and I'm really keen to follow that on. You know, there's some related work going on. Be good to try and answer the question, what is the problem exactly here that we're trying to solve before solutionizing it. Unfortunately, I'm not there in the IETF this week. I'm a remote participant, but if people have emails, I'd love to follow that up. And the thing I'd like to kind of leave with is can we continue to distill down things? Is there, you know, Catherine presented brilliantly stuff I would have said already, so I tried to come at this from a different angle. You know, is there some kind of features of multiplex flows within, you know, with an ability to pick congestion flow control as needs must or as desired within a single connection context that's always secure, and that this is a really simple and performant way to initiate those flows with minimal overhead. You know, HTTP Connect was one way to do it that requires round trips. There might be a simpler way, with, you know, using more of a binary framing, a native approach to these things, that delivers some wins over the old ways of doing things, and that having everything within one connection as opposed to distinct TCP or UDP connections, to call them that, is there an ability to clearly relate those things, have them more, you know, a higher barrier to entry to track them or identify them, but also make things easier from the application perspective, that things that have a shared fate can be cleanly torn down as and when needed. And that's all I have.
Okay, thank you very much. Any questions on this part? I actually go back to like one of your first slides for a second. So if you haven't heard or read those two drafts, please do so and provide transport feedbacks to the authors. I think that would be really important. I don't see anybody in the queue. So Lucas, if you want to join the discussion later, you can join the Meet IQ queue again, but thank you so far. And we go to the next presentation.
So I'm going to talk about the impact of encryption on performance-enhancing proxies. So in the olden days of TCP, there used to be this family of middle boxes called PEP. If you don't know what they are, or if you want to refresh your knowledge about them, you might want to take a look at these two RFCs. 31, 35, 34, 49, they're pretty comprehensive and in-depth analysis of the whole space. But in a nutshell, what the problems that these boxes solve is when you have your transport path crossing one or more low-quality links, and for example, one with height loss or a very variable latency, or if you have highly asymmetric links, for example, with narrow upstream, is the case of satellite. Then you put one of these boxes, or two, sometimes, at both ends of the weak link, and let it split or spoof the TCP connection and perform a number of tricks that include ACK manipulation, decimation, reconstruction, flow control manipulation, header compression, latency split, and let it fix the problem. So Ben suggests to provide a concrete example of these boxes and what do they do in specific scenarios. So I'm coming with the mobile example, but I suppose the satellite people will have hundreds of these examples to provide to the discussion. But from a mobile perspective, what happens is that often the air interface freezes, and then the upper layer sees it's complete freeze of the channel because there's a non-congestive loss on the air, and the lower link protocols in the 3GPP stack actively try to retransmit, right? So they operate on roughly 10 milli boundaries, right? So they try 1, 2, 3 times at 10 milli intervals, and if the specific configuration, so say your multipath fading situation, or the obstacles doesn't remove within that short interval, then what happens is that the freeze can last longer than the typical RTT, and so the TCP sender on the other side of the world thinks that the path has lost the segment, so retransmits, and this is the cliche of this previous retransmission. The loss has been repaired then, and then you have the other layer trying to repair again, and so completely wasted thing. So what these boxes do in this context is they provide. So what they do is they buffer data right from the sender. They hack the sender, and then when the link is back to normal, they smooth the data out to the receiver, and with this providing the impedance matching right at the point where the mobile network and the wired link connect. So without the PEP, the sender would probably throttle, so you have a stall in the congestion window, or a reduction in congestion window, so the throughput, and in general the good would decrease. So these boxes are middle boxes, of course, so the typical caveat applies. In particular, they optimize the current application at the expenses of the future applications, and their precise behavior is not clearly specified, right? So that's the problem, the typical problem with middle boxes. They can break, depending on how they are designed and built and operated and upgraded, they can break the path badly, but even more, they can break paths only partially. So for example, if one of these middle boxes want to optimize always, what happens is that it needs to understand the end-to-end semantics always. And so if you are negotiating an optional bit of semantic on top of your base TCP connection, and that the guy doesn't understand that thing, it will probably eat it up. And this is it has precluded the evolution of transport, right? It's been one of the major causes of ossification. Okay, so encrypted transport to the rescue. If your transport header is protected, so for example, if your transport is an encrypted transport, or equivalently, if you have an encrypted and/or authenticated encap for your transport, that means that the PEP cannot do anything it does normally. So it can do the header compression, no ACK tricks, no RWIN, no sequence number manipulation. So the functions are completely inhibited. So we have this original problem that the PEP solves. So you have problem one, PEPs. Then PEPs create another problem. Then encryption solves this problem, but doesn't solve the other problem, right? So the top level problem by itself. So a few questions to try and articulate a bit of discussion around this thing. First of all, is PEP a valid approach still? So in terms of the problems that it solves, are these problems still relevant? And if yes, if these problems are still there, can we solve the same problems with other techniques? And if not, or if yes, but partially, so if PEP are still needed, so how does a modern PEP look like from the perspective of the endpoints? We know that it must be explicit at this point in time, because it must terminate the security association, so it has to be visible to one or both the endpoints. And the second point is, should the new transport take PEP into consideration at design time? Doesn't seem to me that Quick did this effort, right? But in particular, the problem with Quick is that it collapses the two security association, the application level security association with the transport level security association. So you cannot split the transport from the end to end from this perspective. And to just close the loop with the hint and helium discussion, there seems to be here a space that is worth exploring to understand what we can achieve with the hint and helium in this context, and some research space in terms of, do these two protocols provide what we need from the PEP perspective? So are they providing the right primitives, and if not, what is needed? And then the other thing, which is more open problem for me, is what is the interaction between the inner congestion controller, so the congestion controller from the endpoint to the PEP, so to the proxy, and the outer congestion controller. Sorry, vice versa, and the outer and the one from the endpoints to the end, from the endpoint, from one endpoint to the other endpoint. In particular, under diverse links and user mobility models. So they should be characterized properly before we can say, okay, this is a valid set of tools that we can use in the PEP context. And the third thing is, one thing that is nice in Helium is this in-band control channel that seems to be an interesting bit to be used to exchange cross-layer signals, for example, from 3GPP stack deep down and say in the air interface to the transport. That would be a very nice path to provide these things. But yeah, I think this is the discussion scheme that I wanted to provide.
Hi, Stuart Cheshire from Apple. I had a minor point on one of your earlier slides. I don't know which number it is. You talked about typical round trip time. You talked about spurious retransmission. There you go. I wanted to point this out because this is a common misperception or maybe misrepresentation. The way a transport protocol like QUIC or TCP works is it doesn't retransmit when the average round trip time comes, because if you think about it, the round trip time distribution is like a Bell distribution or some shape of distribution. And if you retransmit it every time you hit the average round trip time, on average, you'd be retransmitting too early 50% of the time. So all of these algorithms take the variance or the standard deviation into account. So, so if you have a link that is very variable, that ought to be reflected in a larger standard deviation so that you have a broader bell curve. You still should be tuning your retransmission timer to be 2-3 standard deviations out so that those false retransmissions are rare. That's just one comment that often the way the salesmen who sell these performance enhancing proxies sell them is with this oversimplification of see how stupid TCP is, we can fix it. And the reality is not that simple. My other observation is when IPv6 started rolling out in volume, all the measurements confirmed that its performance was measurably better than IPv4. Not twice as good, but somewhere between 10 and 30% better performance. And it's hard to know for sure why on a network as big as the internet, but one of the speculations was that it performs better because none of the performance enhancing proxies support IPv6.
Spencer, we take
Spen-
Ben.
Spencer Dawkins, and speaking as the former chair of the PILC working group that produced the RFC on PEPs. The date on that RFC is 2001. Most of the work was done significantly before it was published. We can talk about why. And like, it seems like to me, yeah, I can have opinions about this, but I think what I want to say here is that it seems like we could talk about whether what the right thing to do was every 20 years or so, whether we needed to or not.
Stop. Wait a second. We have
Sure.
Ben in between, so we take Ben now.
Hi, can you hear me?
Yes.
Great. So this is Ben Schwartz from Jigsaw at Google. And I wanted to agree and disagree with something that Thomas just said. Thomas said that in a post-PEP world, or in a vision of PEP for quick-like protocols, the proxy has to be explicit. I agree with that. And he also said that it has to be explicit because it terminates the security association. At least that's what I heard. And I think I disagree with that. So I would like to propose that there are at least parts of the solution space where the security association remains end-to-end from client to destination, and there is something else going on that wraps around the encrypted transport and possibly introduces a second congestion controller and couples the two congestion controllers in the right way, in a way that allows us to avoid terminating any crypto from the end-to-end stream in the middle.
Ben, so sorry, yes. When my voice get garbled, I didn't want to imply that the end-to-end security association is terminated at the proxy. On the contrary, but there's a security association that needs to be terminated at the proxy, and but this doesn't have anything to do with the end-to-end thing. It must be completely explicitly separate.
Cool. So then we agree on that.
Okay.
I also want to, since I have the mic, I want to just take this chance to say a little bit about this concept of explicit, because I think there's, we treat client often from the network perspective, we treat the client as a monolith, but clients also have components within them. So you can imagine, I can imagine a world where apps, for example, aren't aware of the presence of this proxy, but some deep system library, or maybe even the kernel, is aware of the presence of the proxy and is making some adjustments in order to work with it.
Thanks.
Martin Duke from F5. Can you go to the next slide, please? Sorry, whatever the question slide is. There we go. Okay. So I think the problems are still relevant. These links still exist. It is possible. I mean, there are certainly, there's another way to approach it, which is developing a congestion control that is truly adaptable to all link types. I think that's an open question if we have that or not. But regarding the PEP specifically and if they're needed, so we've in Quick we started with this no middle boxes approach. We've already bent the rules 1.5 times. We've already decided that there must be some ability for stateless load balancers to do things. And secondly, there's talk now about anti-DDoS devices sending retry packets. So we're trying to preserve this notion of explicitness, as a couple other people have said, rather than have it be transparent as it is in TCP land. The other thing I'll say is this will not happen in V1, but there is talk about separating, just chatter at this point, about separating the keys between the transport stuff and the actual application traffic for reasons of diagnosing. For after the fact, you can provide the transport key to whoever is going to analyze your network problems without sacrificing your application security. That might be a framework that would enable some sort of explicit some sort of explicit PEP interference in the network with where the client to allow that.
Could I ask a AD interrupt question? Is there anybody that's in line that's going to talk about specific questions on this presentation, or have we moved to open discussion? You guys have specific on this? The guys that raised their hand? Okay, well, I'm just going to put up the slide that says we're on open discussion. Yeah, okay.
Go ahead.
Gary Fairhurst, thanks, Spencer. I'm not sure the answer to the question, so I'll continue. I was one of the original authors of one of the RFCs that was put up. John Border, the other RFC leader, and the PEP spec always said explicit was better. So when PILT met and talked about this, they said explicit was better than implicit because then you know somebody's fiddling with stuff or doing things. Does it matter today? I mean, that's a good question. So over the past few months, we've been trying Quick over satellite links because we play with those, among other things. And then 90% of the traffic runs slower with Quick currently, just because probably Quick was never designed really for satellite links with BOD and RRM functions underneath. Now, Quick could be designed better, and we could fix it here. If we fix it here, like Tom suggests, yeah, it'd be good. If we don't fix it here, then we've got a problem, because for some people, 95% of the traffic will be slower, which makes Quick undesirable. So how are we going to deal with this? I mean, this sounds like an IETF activity. I'd really love to see it happen.
Yeah, I'd just like to echo that. What John said when he was talking to me back in London was that they were getting like an order of magnitude slower throughput rates on testing then between Quick and TCP. So, you know, the easy answer there is just block UDP, or just block Quick, you know. And that's an algorithm, and we were wondering if there might be better algorithms.
Okay, so coming back on that particular one, we got a factor of 3 slower. John Border was using much higher speed capacity links, 100 megabits, which is where we should be going. So the problem gets worse as you get higher speed.
Cool.
Hi, Colin Perkins. Hi, Colin Perkins. So just to follow up quickly on that previous discussion, I think we need to be a little careful drawing conclusions about quick performance compared to TCP performance at this stage, because we're comparing very new, unoptimized, and unfinished quick implementations with TCP stacks that have had 20 or 30 years of tuning. So yes, the quick performance will improve over time. On the explicitness issue, I'd like to draw people's attention to the PERC working group, which is doing a multi-level encryption scheme to allow middle boxes to do semi-trusted processing of some things, which looks similar to some. I mean, it's addressing a different problem, but it's in a way which seems very applicable to these. The proposals to allow the middle boxes to do header processing but not see the content. The same ideas would probably apply to these sort of proxies as well.
So we have 5 minutes left. I think we can cut the queue, and please make sure that you stay in a few minutes.
Lorenzo Colidi. Are the problems it solves still relevant? I mean, yes, I wrote one of these for my home network because I watch video over a 300 millisecond link.
You win.
So had to write 2 of them, put one at each end, just like this says. And of course, it only works with TCP. Now, but to take a step back though, if we go back to the previous 2 or 3 slides ago, sorry, which was the what I wanted to come back was the freeze is typically longer than the RTT. That slide there. Right, that. So I submit, and people are going to start throwing stuff at me because it sounds really stupid. I submit that this is not a transport problem, okay? Now, this is an IP layer problem. What we're trying to tell the sender is, if you're queuing packets to this destination, they are going to be delayed. This has nothing to do with any particular transport session. It's a queue management problem, okay? So if, why is this not done why do you have to break the encryption? Why do you have to do it in an individual transport session? You just need, bear with me, an ICMP message that tells the source, hey, this thing is backed up. Wait, don't take this as loss, right? And it's just a hint, right? So, like I said, sounds really stupid. Let's think about it.
This message existed and we deprecated it because you can't trust it, right?
Yeah, I agree. But why? But we should look carefully at why we deprecated it and whether the reasons are still current today. Now that we know that middle boxes have really, really serious considerations for ossification and for security, and also with that decision may not be the right decision anymore. And we should, if the facts have changed, we should change our minds.
Right, and so to me, one of the key things that you were just pointing to there is that this is a conversation we need to have, and we need to not have it while we're trying to standardize a specific protocol. So that was the point in bringing this to TSV area, so we could have the broader conversation with people who are not trying to finish quick and mumble months. But thank you for the observation, and please talk to me in the hall about it because I got more to say.
Michael Abrams, can we go back to the asking slide? Or actually, it might go here as well. I would just like to point out that some middle boxes today that are in wide use does MSS clamping on TCP, for instance. This is a signal from a network device saying, I think you should do this. So there are a few of these kind of signals, and I think Lorenzo's point here was another one, is sometimes you actually want devices on the way to be able to put bits or stuff into the packet as it goes by. So having transport header encryption where the network knows nothing, well, actually, sometimes it might be good if you know something, that the network can tell you something in the packet as it goes by. So when you design a transport protocol, I actually think there should be some network should be able to influence something as the packet goes by, and I think this should be something that is done in all transport protocols. There was a tunneling protocol, but like a few years back, I saw which had explicit this part the network just can see, and all the rest is encrypted. I think this is a good thing.
Hi, Chi Jin Soo from Hughes. I work for satellite operator. So, I mean, we don't want to have a middle box or PEP. I mean, it costs some money or resources. But the problem is, as you encrypt the traffic header, and the performance degrade significantly. So with currently in a satellite show, we show that with the TCP PEP, the transfer rate can be up to 200 megabit per second. If you run quick with the current congestion window or 2,000 packet, you can do the arithmetic, and it turns out that only 20 megabit per second. It's a 1 order of magnitude lower. So I think the solution, I mean, we don't want PEP or middle box. The solution should be, I mean, which should be designed such that it works for all types of link, including the satellite link. Satellite RTT, even the physical layer delay is 600 milliseconds. But in a busy hour, it can be as long as 1 second. And there's two issues. One is the congestion window, and you can fix with the adaptive congestion window. The 2,000 packet is not enough. The second thing is a packet loss. It's too late, I mean, RTT. So, I mean, the best for us is which can accommodate the design such that it also works for satellite link too. Thank you.
So we did cut the queue where at the end of the time of our session, we would quickly like to announce before everybody's leaving that we have office hours later this week, which are on the slide now. So if you want to talk to two of us, you can do this later.
And if anybody wanted to talk to us about possible BCPs on PEPs or anything like that, just in case anything like that entered your mind in the last hour, we might both be very interested in that conversation.
So if you really want to go on with questions, we can do that. But like the break officially started now.
Yeah, and I actually need to leave. But talk amongst yourselves. You got all week.
All right, well, people are looking at me, so I'm going to make my comments anyways. You can get up and leave. My feelings won't be hurt.
Aaron will always do the right thing, whatever that is.
So I want to thank Lorenzo for his comments because it made me think that one thing that's really changed since we did this 20 years ago is queuing in the network is getting smaller. Buffer bloat, I think that's a substantial change, and that really made the problem worse in the TCP SAT days. Another thing that we've been talking about more recently that's relevant to this is the SPUD PNRG notion of signaling from the network to the end system, which I think is a little bit of what Lorenzo was hinting at, or at least it's related to it.
Yeah.
And so I think this might be a topic to take up in the PNRG, but I think that this is a good time to revisit this topic yet again. And so my ask to the ADs is you figure out where the best place to have the conversation is so that we don't have to have it in every working group this week or indefinitely.
We would be unhurt by the possibility that this conversation happened on the TSV area list. To at least start there.
Sure. Nalini Elkins, I'm going to keep it really brief. Come to IPPM because our PDM and MPDM work really concentrates on this. So advertise.
All right, Aaron, maybe get up last second. So I want to echo back what Stuart said earlier, right? So nobody's debating that PEPs help in certain cases, right? There's ample evidence of that, and they continue to help. The problem is that many of them get put in and then they rot. And so you do not know whether there's a PEP that actually helps you on this path or whether there's a PEP that limits your performance on this path, right? And that is sort of the fundamental problem. So, if we can solve that, right, I think people would be very happy to talk more what Quick and PEP can do in the future, but you can't know, really, right? And everybody wants to believe that the network is well managed and these things are carefully orchestrated. They're not. Not all of them. You know this.
So Lars, an explicit way to configure your PEP or discover your PEP and attach to your PEP would be the solution for this, because you can disable that if you want.
It was very fast. Can you say this again?
The explicitness of the PEP.
Yeah, as Marco Coyo, one of the co-authors, 3135, one of the key messages that we made there is that PEPs, if you use them, you should make them explicit.
Yeah, so I heard large agreement about
Explicit
this one.
is great. I still, even if I know that it's explicit, I don't know whether I should use it or not.
Well, you can measure.
So I think we are in the break right now. So if you want to keep discussing, just
they should not be just
circle
explicit,
around
they should
us
be
and have the
optional.
discussion there. Thank you very much, everybody. See you later this week for sure.
So what did you say?